Hallo, it's Dumplet here. Here's an item on floor functions. So here we have the last item, item 25 of the recent 24th Philippine Mathematical Olympiad qualifying stage. So give this item a try. And if you're ready for it, let's talk about the solution, right? So obviously credits to the Philippine Mathematical Olympiad for this item. As usual, pause this video if you'd like to give this item a try. And if you're done, let us dive into the solution. Okay, so first observation, I guess, the question is indeed pretty long. There's a lot of things to digest, but essentially we do have a function f of xy, and m is the maximum of the floor of x and floor of y. So capital M and small m are the max and the min respectively. We do have a range of values for x and y, and we do have something that we want. We want f of xy to be less than or equal to 2. And let's talk about the rest of the question later. Let's just actually go back for, let's just actually understand the numerous details in the question. So, well, first of all, we want to make sure that the f of xy over here, we want to make sure this is less than or equal to 2. 2 is not that big of a number, so obviously the product here, it should be pretty small. So let's try to check as to what we should be able to do. Now, what's going to make this function grow? What's going to make the function be smaller? So let's just recall for now that m, capital M, is going to be the bigger of the floor of x and the floor of y, and small m is going to be the minimum of the floor of x and the floor of y. So how will capital M grow? Well, capital M will grow if x or y is growing, obviously, because it's the maximum of those two. So that's going to mean that, well, obviously this first square root, it's going to get big if x and y are big. Right? That's the first observation. Next, let's talk about the second expression. How will this expression become big? Now, we can't just say that, okay, x and y become big, because, well, if x and y become big, well, small m, even though it's the minimum of these two, it's going to be bigger as well. So we could see that, well, this thing doesn't really depend on the values of x and y in itself, but we can kind of make the analysis that, well, let's just say x and y, if they are very close to each other, let's just say x is equal to y, for example. If x is equal to y, then, well, obviously m, the small m over here, is just the floor of x and the floor of y. So if x and y are very close to each other, this part will be small. The yellow part will be small. So the yellow part would get big if x and y differ by a lot, right? So I'm just going to take like a random case. Let's just say x is like 10. Then let's just say y is 100, we could try to see that, okay, well, capital M is going to be big, obviously, because of the fact that I made like y to be 100, but this expression would also grow because, well, small m is just the floor of it's just the minimum of the floor of these two numbers, so small m would be 10. And you can kind of see, for example, now that the small m is 10, you guys can kind of see that the consequence of x and y being very far away from each other is going to make that function grow as well. So that's going to be like the basic insights. I'm not really solving anything yet, but just some insight as to how the function behaves, because it is hard to visualize what this graph would look like. And if you take a look at the question, we want to actually get like areas or regions based from the graph, which is a little bit difficult, knowing that we have no idea what this graph looks like. We don't know what this graph looks like, but that's okay. We just did some observation. Now, on the next few parts, it might be obvious to some. You guys might probably done it already during the actual competition. And well, I'm just going to show you like how I kind of got to the analysis that I have and the nice conclusions. But what I did is I kind of considered cases on the values of the respective floor functions. Well, primarily because the capital M and the small m, they do depend on the floor of x and the floor of y. And I just wanted to see how the graph would, how the function would behave, because I have literally no information about the graph. So what I decided to do is just to take a random example. Let's just say floor of x and floor of y differ by 2. Now, because I realized that just taking note of the values of x and y wouldn't really help me much, but if I know the difference of x and y, I could be able to take into consideration the behavior of this part as well as this part. So I'm going to make an assumption though, because I kind of see that if I switch x and y, nothing is going to change, right? If I switch x and y, well, obviously this part becomes y, this part becomes x, but the capital M and the small m, they are still the same. I just interchange the two things. So let me just make the assumption without loss of generality. Let's just say x is greater than or equal to y. And obviously that's going to mean that the floor of x would be greater than or equal to the floor of y. And that's going to allow me to do something nice because, well, I know that capital M is the maximum of those two floors, and the small m is the smaller of, obviously, of those two. Well, capital M would be floor of x, small m would be the floor of y. Now, if the floor of x and floor of y differ by 2, this is what's going to happen to the function. So f of xy, it's going to become square root of, well, capital M is floor of x, so I could just write this down. And the second part, actually, I could write this a little bit interestingly because, well, it's just going to be x plus y. Take a look here. X minus the floor of y, obviously that's positive, right? This is obviously positive. And then y minus the floor of m, that's obviously non-negative because I think it's pretty obvious that any variable or any number, it's going to be greater than or equal to its integer part. Okay, so I could conclude from here that x plus y minus twice the floor of y. Or I could just write it as x minus the floor of y plus y minus the floor of y. And what's important here is to use bounding. Okay, now obviously the floor of y, it's going to be greater than or equal to 2 because of the range of values given here, x and y being between 2 and 2022 inclusive. That's going to tell me that the floor of y is greater than or equal to 2. But that's telling me that floor of x, based from my kind of testing of the case here, that's going to mean that floor of x would have to be greater or equal to 4 because the floor of x and the floor of y, they differ by 2, which means that the first part, if I take the minimum possible value, let's just say floor of x is 4, this would be greater than the square root of 20. So this would be greater than or equal to the square root of 4 times 5, so 20. Next, I could try to take a look at x minus floor of y. Now, floor of x being greater than or equal to 4, that tells me x is at least 4. So the green part, it's going to be greater than or equal to 2. So the x minus floor y part. Now, obviously, for the y minus floor y part, that's going to be greater than 0, greater than or equal to 0. But you guys can kind of see the point. F of xy, I just used bounding here, so the equalities might not hold. But from my observation, the f of x comma y here, it's going to be greater than or equal to square root 20 times 2. That's going to be greater than or equal to 2 times the square root of 20. Based from just my analysis here, I just randomly made the floor of x and the floor of y differ by 2. And this is actually what I realized. I realized that, well, at the floor of x and the floor of y, I just made the difference 2, which is not that big. And that actually is impossible because, well, I want f of x, y, I want this thing to be less than or equal to 2. So I just decided to consider the extreme case. What if I make the floor of x and the floor of y equal to 1? Differ by 1. So that made me want to generalize stuff. So I'm just going to say that I'm going to consider the floor of x and the floor of y differing by at least 1, right? Now I just kind of saw, I saw the condition, I saw the restriction here. I saw the thing here with the difference of 2. It's not going to work. So I kind of realized that, I think I could kind of show this one. If I could show that the floor of x and floor of y differ by at least 1, and maybe say if it's true or false, or if it's possible or not possible, that's going to help me get closer to the answer. So I'm just going to do the same thing again. I'm going to say without loss of generality, floor of x is greater than or equal to floor of y. So Floor of y would be greater than or equal to 2, and then floor of x would have to be greater than or equal to 3 because they differ by at least 1. So, all right, I can get the capital M. Capital M would be greater than or equal to 3. It's because it's the floor of x. Small m is greater than or equal to 2. So the first part, the square root becomes, so f of xy becomes the the square root of floor of x times floor of x plus 1. And we could use some bounding. This thing is obviously going to be greater than or equal to square root of, well, we know the smallest possible value for the capital M. So 3 times 4 over here. So it's going to be greater than the square root of 12. And then in the second one, well, small m is going to be the floor of y. So same thing, I can say that this part would be x minus the floor of y plus y minus the floor of y. Again, I could remove the absolute values because I'm pretty sure x minus small m is positive and y minus small m is non-negative. And all right, from this condition for the x and the y, obviously y would have to be greater than or equal to 2, x would have to be greater than or equal to 3. Again, this is just same stuff as the previous one. X minus floor of y would have to be greater than or equal to 1. Y minus floor of y, that would be greater than or equal to 0. And you guys could see the problem here. Even though I made the floor of x and the floor of y differ by, I'm considering the case where it's just differing by 1. But you guys could probably see that, okay, that's going to cover all the cases because I just kind of shown you guys that, well, it doesn't work for 2. So it shouldn't work for the difference of 3, 4, and so on. So x and the floor of x and the floor of y, even I make it differ by just 1, you guys could see, okay, this thing would have to be greater than or equal to square root of 12 times 1. And that's definitely greater than or equal to, that's definitely greater than 2. So it's not going to satisfy. So if I want the condition in the start, where f of x, y is less than or equal to 2, I have to make the difference of floor of x and floor of y 0. There is no other way, right? Because if it differs by 1, it's too big already. So that's going to be the first breakthrough of our puzzle here. We have a pretty nice condition. We have floor of x to be equal to floor of y. And that's going to allow us to simplify a lot of things here, actually. Because, well, floor of x equals floor of y is just going to mean that, well, m would have to be just both. Both m's actually have to be the floor of x and the floor of y. And I could kind of write this down as the f of xy. That's going to be equal to the square root of, I'm just going to use m still, because m is just the floor of the x and the floor of y, because they're the same anyways. Now, I'm going to write this part, though, a little bit differently, because this part, I mean, yeah, the small m, it's floor of x and floor of y, and x minus floor of x. Again, I could remove the absolute values, because I'm pretty sure these are positive and non-negative anyways. So I could say that, well, this part is essentially, so you guys could recall the fractional part of x in some of our previous videos. And now I'm essentially considering the fractional part of x. And now, I have a pretty interesting equation now. I do have this equation. And I wrote this here because, well, essentially I'm just kind of solving the equation now because I want this to be less than or equal to 2. So I want this entire part to be less than or equal to 2. And I divided both sides by the square root of m times m plus 1. And I'm going to reach this point. So floor of x, sorry, the fractional part of x plus the fractional part of y, it's going to be less than or equal to 2 divided by the square root of m times m plus 1. Now, obviously, m here is just, from our understanding, floor of x, which is just the same as floor of y. And we want, going back to the question, we want the region, actually. So we want to kind of cover all possible values of, all possible points. So I have to consider specific values, I guess, for x and y. And take a look here. I'm going to consider something in the Cartesian plane. And just as what we've been doing, I'm going to consider for a specific value of floor of x and floor of y, which is just technically considering specific values for m. Now, I'm going to show you some examples here. Let's just say I start with the m equals 2. Now, x and y, they're at least 2. That's why I'm going to start with m equals 2. Essentially, I'm just kind of solving floor of x plus floor of y less than or equal to 2 divided by square root of 2 times 3. Essentially, square root of 6. Now, first thing that I realized is that, well, this thing on the right side is less than 1. And that's good because I guess none of x and y, none of the fractional parts can exceed 1 anyways. And I'm going to just make like a bit of analogy here. It's very similar to solving this one, right? It's very similar to solving this one. And, well, I know what this thing looks like in the Cartesian plane because this will just represent like, okay, if this was an equal sign, that's going to represent the equation of a line. And that's why I'm going to use the Cartesian plane. Essentially, take a look. I'm just considering a specific value for the floor of x and the floor of y. In this case, I kind of considered it to be like the m here. Well, obviously, I did the m equals 2 just to kind of roughly show you how things are. And the nice thing about this thing on the right being less than 1, that's going to mean that, well, I'm going to consider like the line, the equation, the graph of this one. It's going to look like the equation of this line. And it's just going to look something like this. Now, because, well, we know this thing is 1. But I could just kind of realize that, okay, it's going to cover this region. So this equation, this one, the first one here, it's just going to give like a graph of this one. And the shaded region is going to be this. And what I have to do is just to kind of get the area of this one. Now, luckily for us, this region is a right triangle, right? This region is a right triangle. And what's going to be the area? It's just going to be, take a look here. It does intersect, I'm going to say this small red square, at 2 points. It's going to intersect at the floor of x being equal to, well, obviously taking the extremes, because the floor of y, in this case, it's going to be 0. So floor of x being equal to, in this case, 2 divided by square root 6 for the m equals 2 case. But then again, generally, it's just going to be the m times m plus 1 in the square root. So it's essentially that. So we know that this portion is just 2 divided by the square root of m times m plus 1. And that's going to be true for the height over here as well. Okay, and if I try to solve for the area of this green shaded region, it's just going to be 1/2 times base times height. So 1/2 times base is going to be this one. Essentially, I'm just going to square this, right? And that's going to give me 2 divided by m times m plus 1. That's going to be the area of the region enclosed by this equation. Now, I considered m equals 2 here, but generally, it's going to be this for each possible value of m. Now, let's go back to the question. We know the range of values for x and y. We know x and y, they are in this range. So we know that the floor of the floor of x and the floor of y, which is m, it can be 2, it can be 3, all the way until, well, it can be 2022. But it can only be 2022 if x and y, they are both equal to 2022. I mean, that's just an additional point in the plane. It's not going to matter for the area because a point doesn't have area anyways. So we could just kind of consider values of m from 2 until 2021. Again, we're taking the sum of the, the area of the region, which is kind of essentially taking points. And here we have the values of m we have to consider because we know that I'm just kind of focusing on a specific case here, but that's going to be generalized into all the values of m. So consider like all the possible green lines here, considering each value of m. Essentially, what I have to do is to consider this sum, because I know I'm just adding a bunch of right triangles for each value of m, and I'm considering each value of m from 2 until 2021. And this is actually just one of those telescoping series, because you guys could see here, I could write this part as, 2 over m minus 2 over m plus 1. And essentially, I'm just taking the sum of this one from m equals 2 until 2021. So you could try to write the first few terms. So 2 over 2 minus 2 over 3. That's going to be when m equals 2. If m equals 3, it's going to be 2/3 minus 2/4. And you guys could see that I'm going to do this until the last one, m equals 2021. 2 over 2021 minus 2 over 2022. And as I've mentioned, it's going to be a telescoping sum, so everything in the middle cancels out. What remains is just 2 over 2, that's 1. And then 2 over 2022, that's 1 over 1011. 1 minus 1011. And 1 minus 1011, it's 1010 over 1011. And that's the a over b in the start. In lowest term, it's expressible as a over b. So we know that a should be 1010 and b should be 1011. And nicely, the answer is just 1010 plus 1011, giving us a final answer of 2021. And that's how we solve item 25 of the Philippine Mathematical Olympiad. This might not be the most comprehensive solution, but essentially the idea is we're just adding essentially right triangles for each value of capital M, right? But the breakthrough, it's probably realizing that the floor of x and floor of y should be the same. And again, this might not be an obvious thing to everybody, but hopefully this creative this way to kind of solve the question is going to spark some creativity in your solutions and other questions as well. All right, so hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye.